Ladies and gentlemen, welcome to my lecture on Generalized Method of Moments, abbreviated GMM. This methodology is for many finance people is sort of an econometric black box. And in this lecture, I hopefully can give you a good overview on how this method actually works. You might have heard about the law of one price. Yeah? So let's have a look on this equation here. The expectation of a vector y times c is equal to 0. This is our moment condition. And often when you read econometric books or the book from Cochrane, people might be somewhat confused about the notation because they don't really know what stands behind the notation. So the law of one price, what does it tell us? So it tells us that the evolution of cross-sectional returns is dependent on a stochastic discount factor, this xi. So now we might wonder, how can we express this? So what stands actually behind this equation that formalizes the law of one price? So we have to understand that this generalized methods of moments technique, like Farmer-Macbeth regressions, are often used, if applied to financial research, for cross-sectional tests. Now we want to explain the cross-section of assets, for instance. So in this case, the method of moments might be an appropriate tool. If we break down this and we say, okay, our y should be the excess returns of an asset or of assets, then we can, let's say, we want to investigate 3 assets in excess form. Let's say yt1 is the excess return of asset 1 at time t, whereas yt2 gives us the excess returns of the second asset at time t. And yt3 in the end measures the excess return of the third asset at time t. So in this framework here we have want to price the excess returns of 3 different assets. For instance, we can think about small stocks. Y1 might be a portfolio of small stocks in excess form. Y2 might be a portfolio of medium-sized stocks in excess form. And Y3 may be a portfolio of big stocks in excess form. And we want to price these assets here by a common factor denoted as Z. And you see our Z, since we have only one risk factor here, our Z doesn't have a cross-sectional index, it has just the time index t. And what do the 3 equations here, what do they describe? So what we investigate here is the expected excess return of each of these 3 assets, can it be explained by the variation or by the co-movement of each single asset times the discount factor, times our risk factor, Z. In the capital asset pricing model, we have only one risk factor, which is the market factor in excess form. So let's think in this research context here, or in this context here, just for illustration, that our Z is the market factor in excess form, like in the CAPM model. And here we have 3 different assets that we want to price with the market factor. So we want to investigate if the co-movement here describes the evolution of our stocks. And as we see here, it is the same point estimate, it's only one parameter here. Since we have only one risk factor here, we have also only one parameter here. So the exposure here is the same. So in this case, our parameter vector consists of only one point estimator. And this guy here, we can each of these equations here, we can also rewrite it in matrix notation, which we have done here on the right hand side. So for instance, if we consider the second moment condition here, we have obviously three moment conditions because we have three assets here. Our capital N describes the number of moment conditions, and this is 3 in our case. So we can rewrite, for instance, the second moment condition in vector notation, and what we get is this. We have a vector of excess returns for the second asset from 1 until capital T. We have capital T time series observations, and this vector of excess returns should be what? It should be described by the co-movement for each point in time, the excess return of the asset 1 times the risk factor at time 1. So this is also here a simple vector, a vector that captures the co-movement or the interaction, and the interaction is the co-movement of the first asset with the risk factor. And according to our model, this should be equal to 0. What does that mean? It means that the co-movement here from our asset with the risk factor explains the evolution of our test asset here, and it should be on average 0. And what we see here we can rewrite each moment condition in matrix notation here, right? So, and what it tells us is that the exposure, which is measured by this psi, and I think it should be psi. I'm obviously not Greek speaking, but as far as I'm concerned, this should be a psi. So the evolution of the excess returns of each stock is explained by what? By the exposure against the co-movement of each single asset against the market factor. This is what our model describes. And the exposure should be the same for each co-movement. You see, for each co-movement here, we have the same point estimator. So the evolution of each asset's excess returns should be a function of its co-movement with the risk factor. And this should be the same across all assets. So there's obviously the co-movement against the single risk factor explains the cross-sectional evolution of our assets return. So that's basically what our model here describes. And this is what we can test using the GMM, the Generalized Method of Moments technique. What we can also do is we can rewrite these three equations here simply by this formula here. So we see obviously that the y, we can put it outside the parentheses, and what remains is then yti times 1 minus psi times risk factor zt, in parentheses should be equal to 0, and this should be true for all I 1, 2, 3, or for all I from 1 to capital N, and capital N describing the dimension of test assets is 3 in our case. And this is also obviously the number of moment conditions. So in our case, in this framework, the number of moment conditions is equal with the number of test assets. Moreover, if we consider, we want to test, let's say, we want to test the Farmer and French 3-factor model. We know the 3-factor model consists of the market factor in excess form, we have the size factor, and we have the value factor. Size and value factors, and also it's zero cost strategies, yeah, so they are in essence as well in excess form, because the risk-free rate obviously cancels out here, as it's a part of the long and short leg. So in this framework here, we have to remember, if these are our moment conditions here, we have to use the assets in excess form. We test the assets in excess form against zero cost strategies or the market factor, which is also in excess form. Yeah, that's why we have the zero on the right hand side. So we can, if we would rewrite our model in the Farmer and French three-factor model form, if we have three risk factors here instead of one, yeah, we have obviously this equation here. We would use this equation. Now we have here an index. It's not only ZT. Now we have ZT1, ZT2, and ZT3. Yeah? Obviously, ZT2 describes the, or is defined as the excess returns, or as the returns of the size factor at time t, whereas ZT3 describes the returns of the value factor at time t. In this case here, we would operate obviously with 3 point estimates, yeah, C1, 2, and 3, and we can put them into a vector phi, and our phi has in this case here the dimension 3 by 1. It's a 3 by 1 parameter vector, and capital K describes the dimension of risk factors in our model. Yeah? So in this case here, obviously, we would have the dimension capital K is equal to 3. Yeah? So if we would like to investigate 25 test assets, let's say we want to investigate 25 test assets sorted by size and book to market ratio in excess form, and we want to investigate if the Farmer and French three-factor model can describe the cross-section of expected returns using these test assets, we would obviously use this equation here. But then our capital N would be 25, as we would have 25 moment conditions, yeah? Where we then would expand each moment condition by this formula here. Yeah? So in each moment condition, we would have 3 point estimates, 3 parameters to estimate. Yeah? But let's keep things simple, and in our case, for illustration purpose, we focus on only 3 test assets, yeah, and only 1 risk factor, which is the market factor in excess form. So the next step is then that after we have formulated the moment conditions using the expectation operator, that we move on, or that we express our moment conditions in terms of the sample averages. So let's average up everything. So from our, instead of the expectation operator that we would have had here, you might remember, we have now the sum sign. Yeah? So we take the sum, the average of the excess returns of the first asset here. We sum them up, yeah? Sum over t, yt is 1, from yt1, and we sum up over t, and we divide it by the capital T, which is the number of sample observations, and it gives us simply the sample average for the first asset, yeah, which is nothing but the average expected return in excess form for the first asset. And we do the same on the right hand side. We sum up the interaction, yeah, the co-movement of the first asset, yt1 times zt, and we sum up over t and divide it by the number of sample observations. And we know this should be, according to our theoretical model, be dependent, or it should be enter the equation with the point estimate psi. We do the same thing for the other 3 moment conditions. Yeah? So this is the moment condition. This is the first moment condition. This is the second moment condition for the second asset. And the last one is the third moment condition for the third asset. Yeah? And we see already here, we can basically put everything in a vector. Yeah? So this is basically one vector here on the right hand side, and on the left hand side we can also stack the average expected returns, the average returns of our test asset into a 3 by 1 vector. So in this notation, on the left hand side, what we have here is the n by 1 vector, and also here on the right hand side, what we have here is the n by 1 vector. Yeah. So what does the model tell us once again? So this model here tells us, or what we basically formulate here is that the vector of average excess returns depends on the co-movement with the corresponding risk factor. Yeah? So the co-movement describes the evolution of average excess returns. And the factor exposure is the same for all of our test assets, and this is measured by psi. And in order to give you an illustrative example, what does it actually mean here, the co-movement or the interaction, let's consider our three assets here. Let's say we have two different points in time. This is our time dimension here, and we have time t1 and time t2. Let's say that our risk factor, our market factor in excess form measured by z at time t1 has a return of 1%. Let's say that our first test asset, y1, has also the same return of 1%, whereas the second test asset, y2, generates at time t1 an excess return of 2%. And finally, our last asset, the asset y3, generates an excess return of 0.5% given we are at time t1. So then we move on to the next point in time. In the next point in time, our risk factor has a positive return. It generates a return of 2 now. And again, our first test asset, y1, generates again a return of 2, like our risk factor. Yeah, we see it moves 1 by 1. Yeah? So if the risk factor moves up, the test asset 1 moves up as well. So it co-moves positively, and with the same magnitude. Let's say that, and let's have a look now at the second test asset. So whereas the second test asset at time t is 1, it generates twice the return of the market factor. So at time t is 2, what happens now? Well, test asset y2 generates again twice as much the return from the market factor. So it is the same ratio. Here it was the ratio 2, and here it's also the ratio 2, because 2 times 2 is 4. So if the market factor increases by 1%, the test asset y2, it always doubles. So it has 2 times the exposure. What about the third the third test asset, y3? At time t is 1, it generates 0.5 of the return from the market factor. What happens at the next point in time? So the market factor increases from 1 to 2, and the third test asset, the return decreases, it increases as well, but only half of it. So it's the same ratio. It increases only by half of the amount of the market factor. If we would now solve these equations here, this is our next step in order to figure out, is there a psi that drives the evolution of our excess returns? Is there a psi that is the same for all of our test assets? So this is basically the question that our GMM methodology wants to investigate. So what's the average return of our test asset? So for the first test asset, it's obviously 1.5. So we have to add just 1 and 2 divided by 2 because we have 2 times these observations, and that is 1.5. Same manner for the second test asset, obviously 2 and 4 is 6, divided by 2 is 3. And finally, for our third test asset, the average return is 0.75. So, given these equations here, we have to solve, obviously, this equation. 1.5, so the average return of the first test asset, which is 1.5, should be what? According to our model, it is psi times what times, now we have to sum up for both points in time the interaction, so risk factor times the return, which is 1 times 1 times 1 plus 2 times 2 divided by 2 because we have 2 times these observations. You see, we divide everything by capital T. So, and this is, if we solve this for psi, our first equation here would give us a psi is equal to 0.6. Doing the same for the second test asset, the same thing. So the average return, which we have here on the left-hand side, should be 3, because for our second test assets, it's obviously 3, and it should be, according to our model, psi times what? The co-movement, which is 1 times 2 plus 2 times 4 divided by 2. And if we solve this equation here for psi, what comes out is psi is also 0.6. Finally, for the last test asset, where we have the average return of 0.75, we put it again on the left-hand side according to our model, and it should be also psi times what times the interaction summed up divided by the number of times these observations, which we have here. It's 1 times 0.5, 1 times 0.5 plus 2 times 1 divided by 2, because we have 2 times these observations. And if you solve this equation for psi, what comes out is psi is 0.6. So in this case here, obviously our model is right, because we can, the exposure psi describes fully, is psi 0.6, describes fully the evolution of our average returns. So in this case, this model is right. We don't have any error here. But in real life, life is more difficult. So in real life, we might come up with, if you solve these equations here, we might come up with the estimate for psi of 0.5, for instance, if we investigate the evolution of the first test asset and the interaction with the risk factor, and we might solve this equation. What comes out is maybe 0.5. For the second test asset, maybe what comes out is 0.7, and for the last test asset, maybe it's 0.65. So in this case, the average psi would be then 0.62 and not 0.6, what it should be if our model would be correct. So in this case here, in real life, we would have errors. So each equation would generate an error. We have here the error for the first condition, the error for the second, and an error for the third. And the question arises then, is the error, is it significant? Is the error too large so that we have to reject our model? Or is it still in certain boundaries where we can say, well, statistically, this model here is still correct? Now, for some, the question arises, what's the difference between using the GMM estimator or the OLS estimator? So what's the difference between the time series framework and the framework that we just discussed? So if you consider the time series framework, what would we do? We would regress the excess returns of each single asset on the market factor. And we would have this simple OLS regression framework. In this OLS regression framework, our exposure beta against the market factor, so we investigate if the exposure beta against the market factor does this describe the evolution, the time series evolution of our asset? Yeah, so it's a slightly different question that we ask here. So here it's the does the linear exposure against the market factor, does it explain the evolution of our test asset? If so, then our alphas should be statistically 0. And for those of you who are familiar with that model framework, with the CAPM, the capital asset pricing model, we know that the beta is nothing else than the covariance between the risk factor, in this case the market factor in excess form, and each test asset divided by the variance of the market factor. So it's in some sense, this is the similarity between this framework and the GMM framework. So in the GMM framework, we have looked directly on the co-movement. And in this framework here, what we would do here is, so we can think about it like this. So if the psi and the GMM framework is statistically significant, in this case, what does it mean? It means that the average co-movement across our asset has explanatory power on the variation in cross-sectional average returns. Okay, so in this case, we might expect that the beta, if we have many test assets, that the beta should be statistically significant as well. If we have many test assets, it could be that some of the test assets, that the beta might be not significant. Let's say we have 100 test assets. It could be that for let's say 8 test assets, the beta is insignificant, but for 92 of our test assets, it is highly significant. And if the psi is significant in our GMM framework, we might expect that the beta, which also measures the co-movement, but somewhat standardized because we divide it by the variance of the factor, that the average beta should also be significant. So that is the commonality of these two different approaches. Though we have to remember that here we want to describe the time series evolution, and in the GMM framework we have a look at the averages. We want to describe the variation in the average returns. So the next question arises: how to derive the GMM point estimator? We are still interested in estimating the psi given our data. So, and this is how it looks like. So let us first define matrices here. Let us define the matrix capital Y, which is the matrix that consists of our test asset. And this should be a capital T by n matrix. So in each column vector contains our test assets. So in our case, we have only 3 test assets. So our matrix capital Y is simply a T by 3 matrix. And each vector in our matrix contains the excess returns of each test asset. So it's very simple. What next? We have the matrix of our risk factors in excess form. And in this notation, I define this matrix as Z, capital Z matrix. And this matrix has a dimension capital T by K. So in our case, it's very, very simple. This is just a vector. So in our case, the Z matrix is simply a T by 1 vector. But again, we can expand this framework here. Once we have defined the matrices, the formula doesn't change. The formula is the same, irrespective how the dimensions look like. The only thing that we have to ensure is that the cross-sectional dimension of test assets, so capital N, should be larger than K. Okay? So next, in our simple case, the psi is just a number. It's just a 1 by 1. It's a scalar. It's a 1 by 1 matrix, a scalar. But in general, it's a capital K by 1 vector. So again, if you remember, if we would investigate the Farmer and French 3-factor model, and we would have 25 test assets in excess form, then obviously our capital N would be 25, and our capital K would be 3. But in our simple case, we use the CAP-M model. We have only one risk factor, and so capital K is 1. And then we have our y bar vector, our y bar. Yeah, it stacks the average returns of our test assets in excess form into n by 1 vector. So in our case, it's very simple. This guy here, it stacks just the sample averages, this from y1 bar, y2 bar, and y3 bar into a 3 by 1 vector in our case. Okay. So once we have defined our input data matrices, we have to minimize this model here, this equation. Or actually, it's not an equation, it's an expression. So we have to minimize what? This is our moment condition, obviously. Our moment conditions, and this guy here, our moment condition is actually a n by 1 vector. If you think about it, here what do we have here? Y bar, it's a n by 1 vector, and we subtract something from it, and what we subtract, this guy here, is also n by 1. Why? Well, capital Y hat is transposed, so t by n becomes n by t times what? Times matrix Z, and Z is t by k. So n by t times t by k becomes n by k times this point estimator here, this our psi, which is k by 1. So what becomes out then is n by t times t by k times k by 1 is n by 1. So what we have here is the n by 1 vector. We transpose the n by 1 vector, which becomes 1 by n. So this guy here becomes 1 by n. 1 by n. We multiply it with a weighting matrix W. And our weighting matrix W must have the dimension n by n, right? Times weighting matrix n by n times what? We know already this guy here is n by 1 times n by 1. So what comes out of this expression here is a number. We minimize, it's a minimization problem. We minimize this number that comes out. And this depends on what? On the parameter vector psi. So that's the objective, that's the function. What can we do next? Well, we know we operate with averages, with sample averages. So we can rewrite this guy here, because this is capital Y transpose times Z divided by the number of sample observations. So we can write it simply as capital Y transpose times Z bar, because it's the average. So we can then basically, what can we do next? We can multiply it out. We can first take the first term, Y bar, small y bar, transposed times our weighting matrix W. We write it here as our first term. Then we have y bar transposed. No, sorry, we are now here. We take the second term. We take the second term, which is capital Y transposed times Z bar times psi, and this should be transposed. So if we transpose this, we know this from matrix algebra. If we have a matrix product A times B transposed, it becomes B transposed A transposed, right? So we have to transpose these guys and change the order. So this psi comes first. It's then psi transposed times what? Times that should be transposed as well, and we have to change the order. So psi transposed times Z transposed capital Y bar, right? times our weighting matrix W. So, and what remains then, now we have to multiply this out with the parentheses on the right hand side. This is what happens here in this step here. We just multiply out the first term, with this guy here, which we have here. Then we take the second guy, and the third and the fourth. So we have 4 terms here. We just multiply it out step by step. It's very simple. So what we have to figure out then now here is the important thing to note here, or one of the important things that we have to note here, is that this guy here, we know that y bar is a n by 1 vector. Transpose, it's a 1 by n. This is 1 by n. The weighting matrix is n by n. We know this already. N by n. Capital Y transposed, what's that? It's n by t. N by t times t by k times k by 1, right? Because psi is k by 1, and our Z matrix is what? It's t by k. So the order here is correct. So what remains is n is 1 by 1. So this guy here is a number if we multiply it out. And the same is true for the second term here. So both are scalar 1 by 1. So basically we can summarize these guys here as either of these. And let's take this guy here. So let's describe these 2 expressions here by 2 times the second expression, which happens here, which is then the first time term here. So we have to take the derivative of this function here with respect to what? With respect to psi, because it's our objective to minimize this expression here by choosing the corresponding psi. So this happens here. So if we take the derivative of 2 times this expression, what happens here? So we see here only what remains after we're taking the derivative is only this expression here. It's Z, capital Z transposed Y bar times the weighting matrix W times small y bar. And we have to take it twice because we have 2 terms. So this is what remains here after we took the derivative with respect to our psi. This psi obviously disappears after taking the derivative, and then we have to take the derivative with respect to psi also for the final term here. We don't have to take it for the first term here because the first term just disappears because there is simply no psi. So taking the derivative with respect to psi for the first term, it just disappears. That's why it doesn't pop up here. But we have the last term here. And if we take the derivative with respect to psi, what remains is this expression here, but we have to take it twice. And this is something that you can, we know this actually already from, or you should know this actually already from OLS framework, because this is very close to the derivation of the minimization problem for OLS as well. You can, if you don't know that, you might look it up or just try by yourself. It should be very straightforward. So taking the derivative with respect to psi, what remains is this expression here, but we have to take it twice. This is what happens here. And now, because we put it to 0, now becomes, our psi becomes psi hat, because now it becomes an estimate. So what happens then? Well, we have to put this guy here, this guy here on the other side, and this 2 obviously disappears. If we put this guy here on the other side, then we have to take the inverse. We put this on the other side, and then we take the inverse of this expression here. Taking the inverse of this expression, this disappears and moves also on the other side. And this is what happens here. So our GMM estimator, psi hat, becomes our matrix Z transpose capital Y bar times the weighting matrix W times capital Y bar times Z. This guy here is inverted, yeah, times what? Times capital Z transpose times capital Y bar times our weighting matrix W times Y bar, which is the vector of average returns, yeah, in excess form. So this is our GMM point estimator. And in our case, now remember, in our case, this guy is just a vector. Yeah, it's a t by 1 vector because we have only one risk factor. Yeah, it's a t by 1 vector transposed. This becomes 1 by t. Okay, y is a t by k is a t by n matrix, right? It's a t by n matrix. W is an n by n. It's a weighting matrix, yeah, which gives us the optimal weighting scheme that minimizes this problem here. Then our capital Y hat, what's that transposed, it becomes n by t. Then again, our Z is just a t by 1 vector. So this guy here, it's 1 by 1. It's 1 by 1. And if we invert 1 by 1, if we invert the number 3, it's 1 over 3. Okay, so it remains simply a number. And what happens here? So again, our Z vector is transposed, so this becomes 1 by, this is 1 by t, yeah, times what? Times t by n matrix times n by n, because our W matrix is n by n times an n by 1 vector. So what happens here? This is also 1 by 1. It's just a number. So we see that our point estimator in our case, yeah, it's just a simple number, and this is the estimated psi that measures the average co-movement, yeah, of our assets against the common risk factor. The question that remains now is obviously, so what's the optimal weighting matrix that minimizes this objective here, our function, and what's the covariance of our point estimator? Let us first start with the covariance matrix. And the big difference between OLS estimation and generalized method of moments relies is the application of the central limit theorem. So in this case here, we have to rely on the central limit theorem. And from statistics, we borrow this theorem here that the point estimator psi hat minus psi times square root of t follows a distribution, a normal with zero mean and covariance of psi hat minus psi. So this is an application of the central limit theorem, because we are working with averages, and irrespective of the distribution of our data vectors, yeah, so this is what comes out. So this is the huge difference between the OLS estimation and the generalized methods of moment. The application of the central limit theorem. So this makes things quite simple, because we know that the point estimator is normally distributed irrespective of the distribution of our assets in this case. So what we can then apply, the thing is, we are not interested in the covariance of psi hat minus psi. We are interested in the covariance of psi hat. So what can we do is we can apply a simple linear transformation. So we can divide this expression here first by the square root of t, and then we can add psi, yeah? So the real parameter vector. If we do that, what comes out is, we have here on the left hand side, what remains is psi hat, and this follows in distribution, a normal, with expectation the real parameter, which is psi, and 1 over t times the covariance of psi hat. So this is the large difference, and here is sometimes where things go wrong. Yeah? So if you compound, if you estimate, or if you calculate the covariance matrix, yeah, of your point estimator psi hat, you have to divide it by the number of sample observations, yeah? Simply because of the central limit theorem application here. Yeah? And this is important to bear in mind. So, and if we basically do that, so what comes out here, so this is basically what we do. Yeah? We take the covariance. First we divide everything by the square root of capital T, yeah, the number of observations, and then we add our parameter vector psi. So, and you see already what comes here in the covariance operator. We put everything into the covariance operator. So what happens is that the square root of t, everything what is removed. So this is just a number. If we put it first outside, so then it becomes 1 over t. And if we then, so this becomes 1 over t. Let's just do it step by step here. This becomes 1 over t, and it disappears here. But what remains is then in the next step, when we add the psi, what remains is psi hat minus psi. If we then add a psi, what remains is simply psi hat, and this is what we have here. Yeah? So this is basically how we would proceed in this case. Yeah? So the next step is then the point of departure in order to estimate the to compound the covariance matrix psi hat. We go back to the equation of for our point estimator psi hat, yeah, and we know already it's given by this expression here. Yeah, our risk factor matrix capital Z transpose times capital Y bar times the weighting matrix times capital Y transposed capital Z bar. This expression is inverted times the matrix capital Z transpose times capital Y bar times the weighting matrix times the n by 1 vector small y bar. Yeah? So we know this already. What we then do next is, the next step is we plug in our moment condition, yeah? And we add the error term u here. Yeah? So we know our moment condition is what? It's that the average, our y bar, should be explained by what? By capital Y bar times the matrix of risk factors divided by capital T, and this is what we have here defined as capital Y transpose times Z bar, yeah? Times the parameter vector psi plus now the error term. So if we plug this expression in for our small y bar, we can do that and multiply it out, and then we end up here in the next line. Yeah? So this is what comes out. Yeah? We put this in first, we multiply the whole expression here with the first term here. It is what we see here, and we multiply this expression here with the second term here. Yeah? And what remains is then here on the right hand side. Yeah, very simple. But what we see here is that this term here cancels out, because what we have here, that's the same. It's the same like here, but here it's inverted. This matrix product is here on the left hand side inverted, so what remains here is an identity matrix. Yeah? So this term here cancels out. So what remains is then psi hat is equal with what? Identity matrix times psi. And identity matrix times something doesn't change anything. So we can move the parameter vector psi on the left-hand side. This is what happens here. It's then psi hat minus the parameter vector psi, and what remains is the term on the left-hand side, which we have here. So then we know from statistics that the covariance of a vector is defined as what? As the expectation of the estimated vector times the parameter vector, in parentheses, times itself transposed. So we know what is here, this guy here, is k by 1. It's a k by 1. In our case, it's just 1 by 1, it's just a number, right? But if we have the Fallon Flange 3-vector model, this will be a k by 1, a 3 by 1 vector. Times what? Times itself transposed, and itself transposed becomes 1 by k. So we know that this guy here, our covariance matrix, has the dimension k by k. Again, in our case, it's just a number, it's just a 1 by 1, it's just a number, but if we operate with more risk factors in our model, then we have here a larger dimension. The dimension is then capital K by capital K. So what we can then do next is we can plug in, we know that psi hat minus psi is defined here as this expression here. We can plug it in, the first guy. It's the same like we have here, but then we have to multiply it with itself, and we have to transpose it. So we have to multiply it with itself and transpose it. So we have to change the order, and have here the transpose sign. So this is basically what comes out, and we see already. Now remember, this guy, our u, is a 3 by 1 vector in our case, because we have 3 test assets. In general, this guy here is n by 1. N by 1. N by 1 times what? Times 1 by n. So what's in the middle has the dimension n by n. And now we have to think about what w, how to choose w such that this expression here minimizes. So this is now the question. So again, we know already that our W matrix must have the dimension n by n, like u times u transposed. So the dimension is the same. So obviously, the only matrix that minimizes this expression here must be the inverse of this matrix here. U times u transposed. So it follows then, so this matrix here, u times u transposed, this defines the covariance matrix of the errors. It defines the covariance matrix of the errors. And it's defined, we can define it as matrix sigma. And sigma is, again, it's an n by n matrix. It's an n by n matrix. So then we have to choose the W such that it's sigma inverted. Because what happens then, if our W is sigma inverted, if we take the inverse times itself, what comes out is an identity matrix. So the only matrix that minimizes this expression here must be the inverse of the covariance matrix of the errors, which is sigma. And that's, again, that's the product of u times u prime. So if we choose sigma, or if we choose our W to be the inverse sigma of our sigma, what happens then? Let's do that. Let's say our W is the inverse of this guy here. So what comes here? This guy here is the identity matrix Yeah? And we know that our sigma, the sigma matrix, is symmetric, and for a symmetric matrix we know that the transpose is equal with the matrix itself, and the same is true for the inverse. So if we take the inverse sigma minus to the power of -1 transposed, it is the same as sigma transposed inverted, right? So knowing these rules, and this, we knowing that this term becomes the weighting, becomes the identity matrix, and we know that W prime is the same, or W transpose is the same as W, we can take this away here, the transposed sign, right? And we see that the whole expression here becomes the identity matrix, right? Right. And what simply remains is capital Z, which we have here on the right hand side, capital Z transposed Y bar times the weighting matrix W times Y, capital Y transposed Z bar, and this term is inverted, right? And now remember that our W, the weighting matrix, is defined as what? As the inverse of our matrix sigma, and sigma is defined as what? As U times U prime. And now again, if we want to compound the corresponding t statistics, yeah, we have to remember now that we have to divide this matrix here, or we have to multiply it. We have to multiply it with 1 over t, because of this. So now we know we have derived the covariance matrix, we have the point estimator, and now we can do simple hypothesis tests. The question now arises how to estimate this methodology given our input data matrices. Here in this example I have broken down it into 7 steps. So what we do first is we put the weighting matrix W equal to the identity matrix that has the dimension n by n. In our example, we are dealing with 3 moment conditions, respectively 3 test assets. So in our example, obviously, the number of moment conditions correspond to the number of test assets. So we use the identity matrix that has the dimension n by n. What we do then is we estimate the parameter vector psi hat for the first step, like we had earlier, but we substitute the weighting matrix here in these positions here with our identity matrix and get the first point estimator, the point estimator in the first stage. Recall now how we have defined our matrices. So we know that our capital Y matrix collects the test assets into a T by capital N matrix, or in our example a T by 3 matrix. This is what we see here. So the first column vector here corresponds to the excess returns of the first asset. The second column vector here corresponds to the excess returns of the second asset, and finally the last column here corresponds to the excess returns of the third asset. And what do we have to do is that we have to multiply it from the left hand side with the transposed factor matrix Z. In our simple example, it's just a vector because we just use one risk factor. So, and we have to transpose this guy. So this T by 1 vector becomes a 1 by T vector after it is transposed. So if we multiply out this 1 by t vector times a t by 3 matrix, what we get is then a 1 by 3 matrix or vector. It's a 1 by 3 vector, and it simply consists of the sum over t from zt times y1t. This is our first increment here. And the second increment or component of our vector is simply the sum over t from our factor zt times the exact returns of the second asset, zt times y2t, and the last component is the sum over t from our zt times y3t. Yeah? And remember, here we have this bar sign. It means we have to take here the average. Yeah? We're operating with averages. So we have here 1 over t, and here also we have to multiply it with 1 over t. Yeah? So moreover, we know that our y bar vector, it simply stacks the exact returns of our 3 assets into a 3 by 1 vector, or in more general terms, it's a capital N by 1 vector. Yeah? So we have now defined our matrices. We just multiply this out here. This is what our program should do. Yeah? It's a very simple procedure. So what we get in our case, we know already, it's just a number. Yeah, the point estimate is just a scalar, a 1 by 1, and it could be, for instance, 0.58. Just to name some, to have some numerical example of what could come out here. So again, if we would have the Farmer and French 3-factor model, and we would like to investigate if this generalized method of moments methodology applied to the 3-factor model could price, let's say, 25 stocks, obviously then we would have here a 3 by 1 vector. Our psi hat would be then a 3 by 1 vector, and this matrix here would change. Obviously we would then have, because we have 25 test assets in this case, we would have a t by 25 matrix. Here this z matrix would not be a vector, because we have 3 risk factors. This would be then obviously t by 3 matrix, and transpose then a 3 by t matrix. So all this would change, and also here this would be then obviously a 25 by 1 vector, where we stack the exact returns of all 25 test assets into a 25 by 1 vector. So this would happen if we would choose the Farmer and French 3-factor model in this framework, and 25 test assets. But we keep things simple here in this example. So this is what comes out in the first step. The second step is then simply, okay, we know that in real life things are not perfect, so we have an error term. So we want to estimate the error terms. So now we go from the cross-sectional framework back to the time series framework. This is what happens in the second step. We get the first point estimate from the first step and plug it in here. We know that our moment conditions looks like this. So we have the asset vector, y1 for the first test asset, minus the psi hat times the interaction, times the interaction vector, the interaction that collects the interaction between the first asset and the risk factor. So what remains? The residual is our estimated error term. So we have to do it for each point in time. So we have to subtract from the realized exact return for the first asset at time 1. We have to subtract the interaction term, times the point estimator for the psi hat. We do this for each point in time and collect the residuals in a t by 1 vector. Now this is what happens here. So in this, we have to do this for all our capital N equal to 3 moment conditions. And what we will get is we get 3 different t by 1 vectors. For each test asset, we get a residual vector. 3t by 1 vector. So what we can do then is having the estimated residual vectors, we can compound the covariance matrix for our residual vectors, the residual covariance matrix. And this is what happens here. Yeah? We just grab our estimated residual vectors and we compound the residual covariance matrix, denoted here as sigma hat. And for the first step, that's why here is a Roman 1. And it's very simple, you know already, you should know that from basic econometrics course. Yeah. So we have to, the first element here is the variance of the first residual vector, and it's simply the residual vector transpose times itself divided by the number of time series observations. Yeah? And the same is here true for the second test asset. Yeah. So we have here, we have to transpose the residual for the second test asset, transpose times itself divided by the number of observations. And actually here, we have here, it should be a 3 by 3 matrix. Yeah, it should be a 3 by 3 matrix. So we have to add here, obviously, one term. Yeah, so we have, because we have 3 test assets, yeah, so we have here on the main diagonal, we have the variances, yeah, and above and below the main diagonal, we have the estimated covariances between these 3 residual vectors. Yeah. So what comes out here? This must be obviously it's a 3 by 3 matrix. Yeah? A 3 by 3 covariance matrix of the residuals. So what we can do then is, yeah, the third step in our estimation procedure is that we redefine the weighting matrix, yeah, after the first step, and we define it, we know already what it should be. It should be the inverse of that covariance matrix. Yeah? It's the inverse of that 3 by 3 matrix. Yeah? This is our first step. This is our third step in the estimation procedure. Since we have now estimated the first weighting matrix, we can also implement the second stage point estimator for our GMM estimation technique. So I denoted it here as psi hat 2, Roman 2, and it's given by the same equation that we have derived earlier on the whiteboard. Yeah, it's our matrix Z transposed Y bar times the weighting matrix that we estimated from the first stage times the matrix Y transposed Z bar. This term will be inverted. We multiply it with the matrix product Z bar or Z prime Y bar times again the weighting matrix from the first step times our vector Y bar. And let's say, just to give a numerical example, that in the second stage of this estimation, the point estimator for psi hat is then maybe 0.597 or something like that. So what's then the fifth step in our procedure, in our GMM procedure? Well, we do the same all over again that we did also in the first step. Again, we have now new errors, and I denoted the error vector associated with the second stage of the estimation as U hat Roman 2, yeah? So, which indicates the second step of this procedure. So, for instance, the first increment in our time series vector U hat 1, 1 for the second stage is what? Yeah, we grab the exact returns from the first asset at the first time minus now the estimated second stage point estimator psi hat Roman 2 times the corresponding interaction at time t is 1. Yeah? So we do this for all points in time, and what we get is a corresponding error vector, a t by 1 error vector that stacks the corresponding residuals into a t by 1 time series vector. Now, since we have 3 moment conditions, again, we have to do it 3 times for our 3 test assets, and what we get is the 3 residual vectors that have the dimension t by 1. Again, what we can do then is we can estimate the corresponding covariance matrix of our second stage residual vectors. Yeah? Again, what we have is a 3 by 3 matrix, or capital N by capital N matrix, which looks like this. So we just do the same all over again, using the residual vectors from the second stage. Again, what we do then is we know that the optimal weighting matrix in this second step is again the inverse of that residual covariance matrix. So we set the second stage optimal weighting matrix equal with the inverse of this covariance matrix here, and this is again something that any standard matrix program can easily calculate. Yeah. So once we know that, we can compound the corresponding covariance matrix for our point estimator. Yeah? So, and obviously in our case it's just a number, it's a scalar, but if we have more risk factors in our model, the covariance matrix would be much larger. Yeah? So if we have, for instance, if we use the Farmer and French 3-factor model in our GMM methodology, then this guy here, our covariance matrix, would be then a 3 by 3 matrix, right? In our case, we keep things simple. Again, we have just one factor and one point estimator. Hence, we have just one number what comes out here. And now remember, it's important that we use the formula that we derived earlier on the whiteboard, which is Z matrix transpose times the Y matrix bar times our second stage weighting matrix, W hat Roman 2 in the middle, and then again we multiply it with the matrix product capital Y transposed times Z bar, and we invert the whole expression here. And now, important to know, first of all, that's a scalar. What comes out is a 1 by 1. It's a scalar, and we have to divide it by the number of time series observations. So that is where it sometimes goes wrong. So remember that then once we know that, we can estimate the t-statistic, and we can have a look if our point estimator, if it's statistically significant. And how do we do that? We simply take the second stage point estimator, what we got out of here, out of the fourth step, and we divide it simply by the square root of this guy that we estimated here. And what we have to do then is we have to compare the corresponding t-statistic. We know that it's normally distributed because of the central limit theorem. So we have to check if our t-statistic is larger than 1.96, given we have a 5% significance level, which is common practice in empirical finance research. So once our t-statistic indicate that our point estimator, that the t-statistic is larger than 1.96 on the 5% level, we would argue that our risk factor is priced. Yeah? So which would mean in our context, in our framework, that the average co-movement describes the variation in average returns. Yeah? So if the point estimator is 0.59, for instance, it would mean that if the average co-movement, if the average interaction across stocks increases by 1 unit, then the average return is expected to increase by 0.59. So that's basically how you would interpret the point estimator. And we had already a numerical example in the beginning of the lecture. You might remember that. So again, if we have the Farmer and French three-factor model, yeah, and then this whole guy here would become a 3 by 3 matrix, yeah, and then we would be then interested on the elements on the main diagonal, yeah. So the elements on the main diagonal are the corresponding variances associated with our in that case, 3-point estimator. So we would be supposed to grab each corresponding point estimator from the second step and divide it by the square root of what we have here on the main diagonal. Yeah? That's how we would then get the corresponding t statistic. And obviously, this model framework can be extended however you want. Yeah, we can also use the Farmer and French 6-factor model, which was proposed in a 2018 paper. Yeah, using 25 test assets, for instance, or whatever. So we can expand this model framework however we want. Finally, we would like to test our model. So is our model able to explain the cross-sectional evolution of returns? So how do we implement the test? So this is in our framework the 7th and last step. So what we simply do is we collect the estimated average residuals and collect them into a vector. Into here we have on the right hand side a 3 by 1 vector. You see here this u hat bar Roman 2 1. So this is the average, the estimated average of the residual vector in the second stage for the first asset. Analogously, this u hat bar Roman 2 is the sample average of the estimated residuals for the second asset in the second step. And the same is true for the last entry. And we multiply it with, on the left hand side, with itself. So in the middle we see the corresponding covariance matrix that needs to be inverted here. And we use, of course, the corresponding covariance matrix of these residual vectors from the second step. We have to multiply this by capital T, by the number of time series observations, and one can show that this test statistic is under the null hypothesis distributed as chi-square with capital N minus capital K degrees of freedom. So in our case, the number of test assets or moment conditions N is 3, and we have only one point estimator, one parameter to estimate, so K is 1. In our case, we have to compare the estimated test statistic with the critical value of the chi-square distribution with 2 degrees of freedom. And we might know, or we might remember from statistics classes, the chi-square distribution. It looks like this. So we have it goes up here and it has a longer tail on the right hand side. So the critical value of the chi-square distribution with 2 degrees of freedom, and we take usually the 95% probability. So 95% of the probability should be here, and if our test statistic falls into the critical area, which is on the right hand side here, then obviously we would reject the null hypothesis, and given that under the null hypothesis we assume that our model prices our test assets correctly, and we have to reject this model. So if the test statistic falls into this critical area, then we would obviously conclude that our model is not able to price this set of test assets correctly. So now the question arises, okay, why is this test statistic distributed as chi-square with n minus k degrees of freedom? So recall that we were relying on the central limit theorem. We know that according to the central limit, or an application of the central limit theorem, that our point estimator psi hat minus psi times square root of capital T follows in distribution normal, with mean of 0 and the corresponding covariance matrix of C hat minus P. But in the same manner, if we go back to the moment conditions, this is also true for the moment conditions. So the moment conditions, this is obviously in our case, a 3×1 vector, and times square root of T is also distributed as normal with mean of 0, a 3×1 vector of zeros and corresponding covariance matrix of this guy here. If we square this expression here, obviously square root of T becomes capital T, and knowing that the increments here are normally distributed, if we square a normally distributed random variable and sum up the square of normally distributed random variables, what comes out is a chi-square distributed random variable. So this guy here, that's why this guy here, because this is normally distributed, these guys here are normally distributed, and we square them here, we sum them up, and we square them. And what we see here in the middle, we can see it as a kind of normalization. So we standardize these normally distributed random variables and sum them up. If you multiply it then by the number of time series observations, and we have to take into account that we have one parameter is estimated here, so that's why we have subtract this expression here by k, because we have one guy is estimated. So if we have 3 test assets and we would have 2, let's say we have a model where we have the excess market returns and the size factor, then obviously this guy here would be distributed under the null hypothesis as chi-square with 1 degree of freedom, because n is 3, k is 2. So our test statistic would be then distributed as chi-square with 1 degree of freedom. But in our case, we have only 1 parameter to be estimated, and we have 3 moment conditions, 3 test assets. So that's why we have to subtract here, because one of these guys is estimated. We have to take this into account when implementing when checking the corresponding reference distribution for our test statistic. So that's what we can do, and it is very easy to implement in any matrix calculus program, such as Matlab. And this is what we will do next. But before we go there, let's just talk about some assumptions. So the key assumption, or one of the key assumptions in this methodology, in this generalized methods of moment methodology, as opposed to the OLS framework, we remember that in the OLS framework, we were supposed to take into account the normal distribution as an assumption. This is not true anymore for the GMM framework. Using generalized method of moments, we do not need any distributional assumption. So even if our data vectors are not normally distributed, the point estimator follows in distribution a normal anyways, irrespective of the distribution of the corresponding data vectors. And we know, of course, that stock returns are obviously not normally distributed. That's not a secret anymore. Which makes this methodology appealing in empirical research. So the only thing, or the key assumption in this GMM framework, obviously there are some other assumptions that are common sense. Obviously we assume that this guy, the point estimator, that the link is linear and so on and so forth. But the key assumption here in this model framework is that our data vectors exhibit ergodic stationarity. Yeah? Otherwise, we cannot use this method. So what does that mean? So stationarity means, obviously, that we do not want that our data vectors follow a random walk. Yeah? So like stock prices, for instance. So we do not want that. Yeah? And ergodic, what does ergodic means? That the future is like the past. Yeah? So let's say we have a process here that circulates around. So we are here in a bear, then we are in a bull market, then we are in a bear market, in a bull market, bear market, bull market, and so on and so forth. So if we calibrate it long time enough, so let's say we have always about 20% we are in a bear market and 80% in a bull market. So occasionally this can vary. Sometimes we are 70% sometimes in a bull market, and sometimes we are 15% in a bear market. But if we take a very long sample, then we can say that on average we are 80% in a bull market and 20% in a bear market. So this process here goes always back. It well behaves, and it moves around here a long-term average, and this is what we want to have. Yeah? So we want to have a process where we can make inference based upon the past. Yeah? So, and the variance is obviously bounded. It is not circulating wild around like in this case here, where the variance is increasing. We don't want that. We want that the variance is stable. Yeah? So what I would say the key assumption in this model is that the variance of the variance must exist. The variance of the variance must exist. So what does that mean? So we do not want a process that circulates around here, and then it has these kind of very huge spikes that maybe even become larger and larger, even though on the outside it seems that it's well behaving and circulating around some sort of sample average. But this is just if we have a sample. Let's say we have only this data sample, yeah, and everything looks fine here in this small sample. But we will be surprised if we expand the sample, yeah, because actually this process here has no variance, yeah? Or let's say the variance is not converging. Yeah? But we do not see it obviously from the beginning of the sample. So we don't want this kind of process. If we have this kind of process here where the variance is either not defined or it doesn't converge, it's infinite, then obviously our methodology doesn't work out, simply because the central limit theorem doesn't work out. Yeah? Because the central limit theorem requires that we have convergency, so that the mean should converge, and the mean only converges if the variance is stable, right? If the variance is not stable like it is here, yeah, then what do we know about the mean? Not much. Yeah? So this is a very important assumption, the key assumption, I would say, in this GMM methodology, that we want to rule out random walk, and we want to rule out this wild sort of volatility. We want to have processes that are ergodic stationary, that are well behaving, where we can make, where we know that the past at some point in the future will repeat itself. Yeah? For instance, a Garch 1-1 process, as another example. So we know a Garch process is what? Yeah, so we have periods of low volatility, periods of high volatility, low volatility and high volatility, and so on and so forth. So if we have a Garch process, if we are dealing with a Garch process, in standard OLS regression, yeah, we know that we have to adjust the covariance matrix, and we have to account for that also in the estimation procedure. Yeah, we know that our point estimates, or that the variance is different. Yeah? So we have to, because the key assumption, or one of the key assumptions in OLS is obviously that we have the IID, yeah? So that they are identically distributed. But this is not the case here. Here the variance is time dependent. Yeah? It's a conditional heteroscedastic distributed. Yeah. So, but for our GMM methodology, that's okay. This is no problem. So even if the data follows a gauge process, our point estimates follow anyways in distribution with the normal. So we do not have to do any adjustments of the covariance matrix. So that's the beauty of the GMM methodology. So we can deal with much more processes. So the only we have just to ensure that the processes that we are dealing with are ergodic and stationary. Yeah. So the question arises then: what about stock markets, or what about financial markets? Are financial markets, do they exhibit this ergodic stationarity? And here opinions obviously are different. But let's have a look on what Mark Spitznagel, the hedge fund manager, who earned a lot of money during the COVID-19 pandemic, what he thinks about stock markets. Do stock markets exhibit ergodicity?
Financial systems and markets are non-ergodic. They do things always a little bit differently, specifically to trap the timers, the data miners, the naive hedgers.
So as we have heard, hedge fund manager Mark Spitznagel, this is the guy whom you see here on this picture, has obviously the opinion that stock markets or financial markets are non-ergodic. Yeah? So the future is always a little bit different from the past. And here is an article which has been published in Forbes entitled "How a Goat Farmer Built a Doomsday Machine That Just Booked a 4,144% Return." This article has been published on April 13, 2020, and here you see the guy who wrote the article. It's Antoine Guerra from Forbes, and if you go through the article, then you will see that he's the hedge fund manager of a hedge fund called Universa. He has $4.3 billion under assets, and yeah, in his investment team consists of mathematicians mostly, and he has, as of now at least, about a dozen of clients. So here it is described a little bit how his strategy works out. So he buys out of the money put options, obviously, and his flagship hedge fund Black Swan Protection Protocol he earned in March 2020, when stock markets went down, when we had this huge crash due to the COVID-19 crisis. His hedge fund made a return of 3,612% only in this 1 month. Yeah, and again, his strategy is based upon the idea that stock markets are non-ergodic. Why? Well, because from time to time we have these crashes, these huge crashes where 20, 30, 40% of the money is all of a sudden burned. But even though there are some voices who postulate that stock markets are non-ergodic, anyways, people use the Generalized Method of Moments technique and in finance research, and this is what we want to implement now as well. So this is how our Matlab screen looks like. We have on the right hand side the command window, we have the workspace on the left hand side, and let's just implement the Generalized Method of Moments technique in a very simple manner. Let's open a new script here and let's write down the code here in our script file. First of all, we have to import some data. Let's operate with 25 test assets sorted by size and profitability. You see here we have already the Excel file in our GMM folder. We just double click in an attempt to import the data. Matlab is a little bit slowly sometimes, so we have to wait a little bit. So let's import it as a matrix. If you would push the button column vectors, if you would remain it here, then it would import all of these guys as column vectors. But we don't want that. We want the matrix Y, capital Y. That's the matrix notation from our lectures. And yeah, let's import the whole matrix here. So we see it's running from B to Z here. Yeah, we have 25 assets sorted by size and profitability. Yeah, and we see also here that we have 696 time series observations in gross returns. We have gross returns. Push the OK button here, and now we can close with the wizard, and we see in the workspace that we have this data matrix. Yeah? It's 696 rows. The row index is on the left hand side, and on the right hand side we have the column index. So we have 25 test assets sorted by size and profitability. Let's rename this matrix. Let's call the matrix gross underscore return. That we know that we are dealing with the gross returns here. So what else do we want to need? We need obviously the risk-free rate. It's also in the folder GMM, and we have here the Farmer and French factors. So all of this data is downloaded from Kenneth French webpage, yeah, which you can easily access via Google. So let's push here the matrix button, and here everything is basically marked. And let's move this button here to the right, and so that we just have the RF, the risk-free rate, which is here the column G in our data matrix. Again, we have the corresponding time dimension. You see here towards the end of the sample we have a 0 risk-free rate in the US. Again, we have 969 observations, or actually this data matrix has, if we import it, it should be 969 observations, as you see here. Yeah, let's close this wizard again, and let's denote this guy here as RF, yeah, because this is the t/1 vector of risk-free rate. Yeah. What else do we want? Let's just use this size factor as the risk factor. Let's investigate if these 25 test assets sorted by size and profitability can be explained by the co-movement with the size factor. Yeah? So the size factor here in this data matrix is the second guy here in the second column. Yeah, it's this Farmer and French size factor retrieved from the data set that is available at Kenneth French webpage. Let's close the button, the wizard, and let's call this vector here as size. Okay, that's the size factor. Let's also import some other risk factors. Let's import the value factor as well, the well-known value strategy. It's also a zero-cost portfolio, so we operate here in this application only with zero-cost strategies. Yeah. So here's the value factor, HML, high minus low book to market ratio. Let's import this as well. Let's denote this guy here. Let's rename it as value. Yeah. And let's also upload the profitability factor. Yeah. So it's in this matrix here, it's in this column E. You see? Again, let's push the OK button. Now we uploaded this data vector as well. Let's denote it as profitability. So now we have some data vectors here. Let's rename it here as gross returns, because this is plural. So again, let's go back here to the script file. So we could also, of course, we could write everything directly in the command window, but we don't want that because it's easier to write it here and then to run the code after everything is ready. If we write everything in the command window, we cannot make adjustments if we have made an error in the code. Okay, so it's easier to write it here. Always when we want to write something as an information, yeah, we have to use this percentage sign. If it's not a part of the code, if it's just for our information, for some, so that we know what we are doing here. So this is the generalized method of moments. Yeah, the GMM methodology. So first, what we have to do, let's create the excess return matrix. Yeah, the excess return matrix of our test assets, sorted by size and profitability. Again, in this framework here, according to the law of one price, we are operating with our test assets in excess form. So we have to subtract the risk-free rate. Yeah? That's what we have to do, since we operate also with risk factors as zero-cost strategies. All right. So first of all, we have to determine the time dimension, capital T, denoted as capital T, and that's simply the length of our risk-free rate vector. Now we could also write here, obviously, the length of our size vector, or the length simply of y, because it has all of these, as you see here in the workspace. The length is always the same. It's 696 time series observations. Yeah. So now we have defined what is capital T. Let's also define what is capital N, which is the dimension of moments, of moment conditions, and the dimension of moment condition is the same as the dimension of test assets, and that's 25 in our example. Remember, from the whiteboard we had only 3, but now we can easily expand it since we operate with a program. So let's define the excess return matrix as capital Y, and it should have the dimensions, of course, capital T by capital N. Yeah? It has the same dimension like the matrix in gross returns. Now let's define a simple for loop. So for J is 1 to capital N, so we are obviously in the column space, yeah, because capital N denotes the column space. What should we do? Well, we should store in each column J, yeah, this double point here means the whole entry, yeah, and if J is 1, if this is 1, we store something in the whole column 1. And what should we store there? Well, let's grab the corresponding vector in the gross return matrix. Yeah, so you see it's the same entry that we take, the same vector, the first vector, which has the gross returns of the first asset. And what should we do? We just should subtract the risk-free rate, the vector of risk-free rates. So this guy here is T by 1, this guy here is T by 1. So what comes out is a T by 1 vector that we store here in the first vector of our excess return matrix, capital Y. So we end the for loop, and that's it. The next step is then we have to create a vector of average excess returns, right? So you see it was this Y bar, yeah, the Y bar, and it was on the whiteboard it's 3 by 1 vector, since we had just 3 moment conditions, respectively 3 test assets, but in our case it's a n by 1 vector, it's a 25 by 1 vector, since we have 25 test assets. And what should it be? Well, first of all, we have to create a 0 vector that has the dimension n by 1. Yeah, it's a column vector. And what should we do? Again, we operate with a for loop. For j is running from 1 until capital N. We do something in the dimension of test assets. So what should we do? What should we put in entry j of our vector? Well, it's simply the mean, the average, yeah, of our excess returns for the first asset, or for asset J. Okay, and then we end it. So if J is n, obviously, we take the mean for the first column vector of our excess return matrix Y, yeah, and we store it here. Then J goes to 2, and we do something in the second column. We access the second column of our excess return matrix Y and take the mean of it and store it in the second entry as the second array of our Y vector. Yeah, this is obviously this Y bar from the whiteboard. Okay. So next, what should we do next? We need to define the matrix of factors, the factor matrix, right? So define the matrix of factors. And in our simple case on the whiteboard, we had a simple t by 1 vector. We had just the excess return of the market as risk factor. And I said, now, okay, we denoted this matrix as Z also on the whiteboard. We do the same here in order to keep the notation coherent. And let's say we just want to grab the size factor. Yeah? So we can just, this means that we create a matrix, these brackets here, but we actually don't need it because we have just a vector. Okay, so we just can skip that. So now we have defined our input matrices. Yeah, we have the Z matrix, we have the Y matrix. Yeah, remember it's the same notation that we had on the whiteboard. Okay, and the same dimension and the same notation in the dimensions as well. So we have everything is coherent. So what's the first step that we have talked about on the whiteboard? How to implement this strategy. So the first step in this GMM estimator is to compound the you might remember the first step was the weighting matrix W should be the identity matrix, right? And then we estimate the point estimator. So let's denote the point estimator simply as B_1. We know already, since we have just one risk factor here, what we get is just, this is our psi from the whiteboard, okay? That's the psi hat Roman 1, yeah? The first stage estimator in our GMM framework. And here in this notation it's B_1. We know already it's just one point estimator since we operate with only one risk factor. So what was it? So it was this Z transposed Y bar. And bar means it was actually because we were supposed to we operate with averages. So instead of writing Z transposed Y, we can just multiply Z transposed Y with 1 over T. It is exactly the same. So then let's write it here, Z transposed times Y times again 1 over T times Z, no, it was now in the second step, it was Y transposed times Z, right? And this was inverted. Yeah? Remember now, this was inverted. And actually here in between, in the second stage, okay, here would be a weighting matrix W. But in the first step, it's the identity matrix, and the identity matrix doesn't change anything, so we can just likewise skip it here. Yeah. So we are left with this expression here, and we have to multiply this expression with what? With 1 over T times Z, capital Z transposed times Y, right? You can also plug in here a parenthesis sign, but it's not necessary, times our vector Y. And on the whiteboard, this guy here was Y bar. Okay? So we can just mark everything here and paste it here into the command window, and let's see what comes out. So our point estimator in the first step is 0.0731. Okay, so everything works out fine. This was the first stage. And now remember, you have to compare this with what we have derived on the whiteboard so that you get familiar with the notation. Yeah, once again, this guy here is actually in our notation from the whiteboard. It's capital Z transposed times Y bar. Yeah? But it's the same as if we would multiply this just with 1 over T. Yeah? Because we operate again with sample average. So the second step was then what? Well, the second step was that we go back to the time series, framework, and we get the errors. Get the errors from the moment conditions, right? Get the errors for each moment condition. And compute the covariance matrix. Compute the residual covariance matrix. So this was next step, and we store this. We store it. Store the errors. We store the error vectors. The error vectors in a matrix. In the matrix capital E. Okay, this is what we do now. So our matrix capital E is, let's code it first as a zero matrix where we store in the results. So that's what we usually have to do. We have first to create a zero matrix, and then we have to store the results in it. And the dimension is capital T by N. Remember now on the whiteboard we had these three vectors. You had 1, you had 2, you had 3. And all of these vectors had the dimension T by 1. Here we store our 25 vectors in this matrix. This is the same thing basically. So now we do something in the dimension of test assets or moment conditions. So J is from 1 to capital N, and we do something in the time series dimension for for T is from 1 to capital T, right? So and what should we store? So in element T, J in our capital E matrix should be what? Well, we grab the corresponding element in the excess return matrix, yeah. And what do? Now we have to compound the, remember now the moment condition, it was what? It was the co-movement, yeah? It was the interaction of the test asset, yeah, of that guy here with what? With matrix set. Matrix set. It was the same element here. Times our estimated point estimator from the first step. Now, that's all we have to do. We do this for each. We start with this asset 1, and then we do this for each point in time. We subtract from the corresponding excess return. Yeah, so in the first loop, this is 1, yeah, and we do something in the time dimension here, and we subtract from each corresponding excess return element for the first asset the interaction with the risk factor times the point estimator. Okay, remember now, in our case, we have just one risk factor here, so this is 1 by 1. Yeah, this means here, take all elements in our factor matrix Z. Yeah? So multiply all elements in the first row, and there's only one element obviously, with all elements of our point estimator. So this is 1 by 1, this is 1 by 1, yeah? So this is 1 by 1. So we multiply this, what is 1 by 1, with something that's 1 by 1. Yeah? So we subtract something here that is 1 by 1 and store it here. Yeah, so and we do this for all entries until we from 1 until capital T, and then we go to the second asset and we do the same thing. Yeah. So that's what happens here. And now remember, if we have now, let's say, 2 risk factors, then this guy here, there are 2 entries here. Yeah? So in each row are 2 entries, and we multiply the SWOT, yeah, with a 2 by 1 vector. So 1 by 2 times 2 by 1 is 1 by 1. Yeah? So the dimension doesn't change. This is 1 by 1 as well then. It doesn't matter how many risk factors we have. Yeah? This guy here is always the 1 by 1. This product here is always 1 by 1. And that's the beauty here. So we can easily change this. Yeah? We can change the input data matrix, and we don't have to change anything in the code. It does exactly what we want. So that's the beauty here. And after we have done that, so the third step, what's the third step then here? The third step is compute the weighting matrix. Yeah, we have to compute the weighting matrix. Which is the inverse of the covariance, of the residual covariance matrix. Okay, so and that's very simple in Matlab. So we have just to write. Let's denote first of all this weighting matrix as W underscore 1, because this is the first weighting matrix, and that's simply, yeah. So this means now, okay, create a matrix, and what should it be? The matrix should be what? The covariance matrix of E. Yeah. So the matrix E we have here. Yeah. So the covariance matrix of E is a 25 by 25 matrix, right? Because we have 25 test assets here. So, and again, these brackets here means create a matrix. And this is what we do. We create a matrix here that we invert. Because remember now that the optimal weighting matrix was the inverse of the residual covariance matrix. Let's copy this as well in Matlab. And we can see now here, if we go on the workspace, everything that we do here in the command window is saved here in the workspace, right? So we see here all the dimensions. For instance, our y vector 25 by 1 is exactly what it should be. And here, the first weighting matrix is a 25 by 25 matrix. Now, if we double click here, Matlab will spit it out what it is. Yeah, and this is how the matrix looks like. Okay, that's the covariance matrix. And on the main diagonal, yeah, we have the residual variances. Yeah? They are stored here on the main diagonal. So the first guy here, that's the residual variance for the first moment condition. Second element on the main diagonal is the residual variance for the second moment condition. Yeah, so it's very simple. So let's go back to our code. So what we do next is we have to compound the fourth step is then to compute the GMM, the second stage GMM estimator. That's the optimal estimator, right? And we know already how it is defined. It is basically the same like we have here. We can just copy it. We are lazy. We just copy it here. And we include here in between, yeah, as we said earlier, the weighting matrix. Very simple. And also, if you remember from the whiteboard, we have also to add the weighting matrix here. Okay. So let's see what comes out. If we copy this into Matlab, what's the optimal point estimator? It's 0.0323. So let's compare this. No, wait, this is the, now we have overwritten, we have done a little error here. So that should be our second, right? So the first one we have here defined. So let's do this again. Let's copy everything here. And let's compare these two estimators. So the first estimator was what? It was 0.0731, and the second is much lower, right? So it's 0.0323. So, but we still do not know what is if the point estimate is statistically significant, right? So we have to continue here. We have to move on. The fifth step was what? We have to compute again. Compute the errors from using the from the moment conditions, using the optimal as point estimates. Yeah, point estimate or estimates, depending on how many risk factors you have. Calculate. We have to calculate the covariance matrix. Calculate the covariance matrix. Associated with the second stage estimates. And we store the errors of the second stage in matrix, let's call it capital E underscore 2, okay? So that's what we do now. Again, we create a zero matrix first, denoted as capital E underscore 2. It should be what? It should be zeros of the dimension capital T by n, okay? Like earlier, nothing. The dimensions, of course, don't change. Again, we do the same thing actually like before. We can go up and we can just copy this. Yeah, we can just copy this and make some small adjustments here. Paste it here, right here, underscore E underscore 1. We can take this away, sorry. So we can here, we store something in our matrix E underscore 1. And the only thing that changes here is obviously the point estimator, because now we use the optimal point estimator. Yeah, so very simple. Let's copy this into Matlab. Now we have stored it here. It's again, this should be a 25 by 25 matrix, our capital E underscore 2, and it's actually, no, it should be a T by N matrix, right? So it's here. It's a T by N matrix, like our matrix capital E. It has the same dimension, right? But we see already here, the minimum is higher than the earlier minimum from our matrix capital E, and the maximum is higher as well. Yeah, you see the entries, it's not the same. We don't have the same errors. The errors are slightly different estimated. Because, of course, we have obviously here a different point estimator. So next, what we have to do is we have to compound the optimal weighting matrix associated with the corresponding residual covariance matrix from the second stage. Yeah, and again, what is it? It's the covariance matrix of this guy here. Yeah, and we have to invert it. Remember that, very important. So then, next, the sixth step is then what? We have to compute the covariance matrix of the optimal point estimate, or second stage. It's the second stage point estimate. So, and we might remember from the whiteboard, how was it defined? Let's define this matrix as cov underscore b underscore 2. And what should it be? First of all, it's important to remember it's 1 over t. Yeah, it's 1 over t because of, remember, because of the central limit theorem, times what? We have 1 over t, it's now, again, it's the same expression like earlier. It's this Z, the vector matrix transposed times Y, yeah, and Y is the excess return matrix. And it was bar, yeah, we have to take the average. And we can, again, we do it here in our code by just writing 1 over T times matrix Z transposed times matrix Y. Okay? And now we add here the weighting matrix, the optimal weighting matrix W2 that we have estimated from the second step is in between. Yeah, and again, we have to compound this product 1 over T. Remember from the whiteboard again, and now we have Y transposed Z. And we have to invert the overall matrix, right? That was the way how it was defined. Let's copy everything here into Matlab again. And now you might remember that the t-statistic is what? It's simply our point estimator, because we have just one point estimator, divided by what? By the square root of the covariance matrix here. Yeah? And we can write it directly here into the command window, right? So the t-statistic is 2.68. Yeah? So we know from statistics that the t-statistic that is larger than 1.96, given we have a significance level of 5%, indicates statistical significance on a common significance level of 5%. So obviously, this result indicates that the size factor is priced in the cross-section of our 25 test assets sorted by size and profitability. Yeah, this might not come as a surprise, yeah, because our test assets are by construction sorted with respect to size. Size is one dimension, right? So, but does the model basically a good job? Is it capable of pricing the cross-section of our 25 test assets sorted by size and profitability correctly? That is the question. So the seventh step was what? It was testing the model. Is the model correct? If so, the pricing errors should be on average 0, right? So if we take the mean of the matrix capital E underscore 2, yeah, where we store the time series vectors of our residuals, yeah, if we take the mean, we get the pricing errors. It's the average pricing errors, right? Because we are operating here with averages. So let's define small e underscore 2 as the mean of capital E underscore 2. Okay, let's just copy it here into Matlab and then we have a look at what it is. So you see, this is obviously a 1 by 25, a 1 by capital N vector. Yeah, so here we have we can also write plot. Yeah, let's give the plot command. We want to see how the distribution looks like of the errors. So that's how the error distribution looks like across our 25 test assets. Yeah, you see some smaller errors, but also some larger peaks here. Yeah, so the average errors they vary quite a bit here. So that's a row vector because obviously we have in 25 columns. Yeah, we have 25 columns. So if we take the mean, yeah, so we have a 1 by 25 vector. So, but we want to, that's why we have to transpose this guy in order to get a 25 by 1 vector, a capital N by 1 vector. Yeah, if we transpose this guy, we get we change the dimension, right? And that's what we need for our test statistic. So the test statistic lambda hat, yeah, from the whiteboard, you might remember. How is it defined? Number of time series observations, capital T, times our vector that collects the average residuals, yeah, the average, and they should be close to 0 if the null hypothesis is true, if the model is correct. Yeah, these guys should be close to 0. We have already seen that they are not. Yeah, they are not close to 0. But anyways, we have to test it correctly. So let's now we have to transpose our vector so that it becomes again 1 by capital N vector, yeah, because we want a scalar. What comes out should be a scalar here, and we have to multiply it with what? Again, we create a matrix here, and what should it be? It should be the covariance, and it's obviously a command in Matlab. If you write COV, yeah, it tells Matlab to take the covariance of whatever is here in parentheses. Okay, so and what we put in here is obviously the we want to have the covariance matrix of the residuals for our 25 moment conditions associated with the optimal second stage point estimates, right? Recall that from the whiteboard. And again, this in the middle should be inverted, right? We have to invert this expression and we multiply it with this vector of average residuals from the right hand side. So that's our test statistic, right? So let's plug it here into Matlab and have a look at what it is. So here something went wrong. Let's see, where's the error here? So this is t by 1. So this is obviously 25 by 1. That's correct. 25 by 1 transposes 1 by 25. And this guy here, the dimension here is also correct, right? It should be 25 by 25 times 25 by 1. So actually this should work out very well. Let's do it one more time. So and this is what comes out here. So that's our lambda. Yeah, it's 62.28 rounded. So now we have to compare this value here with the chi-square distribution of 25 degrees of freedom. Or actually it's 25 minus 1. You remember from the whiteboard, under the null hypothesis, this guy is distributed as what? Capital N minus K, right? And in our case, N is 25 and K is 1 because we have just one risk factor. So it's 24. We have to compare it with the chi-square distribution with 24 degrees of freedom. And if we look in the statistical table, let's just have a brief look here. So if we have 24 degrees of freedom, the 95%, the critical value for 95% probability is 36.42. Yeah. Critical value is 36.42. So since our lambda hat is larger than the critical value, yeah, we have to reject the null hypothesis. Recall that under the null hypothesis, we assume that this model is correct, yeah, that this model consisting that the size factor alone can price this 25 test assets sorted by size and profitability, yeah, but since our test statistic is much larger than the critical value, yeah, of our reference distribution, we have to reject the model. Hence, we see that our model cannot explain the cross-section of expected returns. So this is what comes out. We can now do some changes here. So the code is basically universal in a sense. So let's say, okay, we want to investigate our factor matrix. Let's say we want to investigate the size, value, and profitability. Okay, so we have now here redefined our matrix, our Z matrix. Let's just copy it here into Matlab and we see what it is. So we have now 3 risk factors. So the question is now, okay, can these 3 risk factors here, consisting of size, value, and profitability, can they price our 25 test assets sorted by size and profitability? So here, obviously, everything remains the same. Yeah, this remains the same. This remains the same as well because we use the same test assets here. This is already changed. Our Z matrix is changed, and now we can just copy everything. We can copy everything like it is, paste it in here in Matlab, and now we get new estimates. So first of all, let's have a look at our estimates, the first stage estimate. Now we have 3 parameters, right? So the corresponding point estimate for the size factor is 0.0867. For the value factor is negative here, yeah. And for the profitability factor, it's basically almost the same like for the size factor, yeah. Let's check the second stage estimate using the optimal weighting matrix. So things change. So the economic magnitude of all point estimators changes, and from the value factor it becomes positive, yeah, and close to 0. So let's now test our, let's get the t-statistics. So what we have to do is, okay, I told you on the whiteboard, so we have to take the corresponding element. Let's take the first guy here. It's the first element in our vector b_2 and divided by the square root of what? Of this guy here, of our covariance matrix. Yeah? This guy here is now a 3 by 3 matrix because we have 3 risk factors. Yeah? Let's check here. You see it's a 3 by 3 matrix, like it should be. So and we have to divide it now by what? Now we have copied everything. So let's do it one more time here. So b_2, the first element, and divided by what? By the first element of this matrix here, right? Take the first element on the main diagonal and take the square root out of it. Square root, SQRT means take the square root. And what we get is a t-statistic of 3.34. So the size factor is still statistically significant. What about the value factor? It's the second point estimate, right? It was close to 0 in the second stage estimation. And it's the second guy on this, in this matrix here, cov_b_2, yeah? This guy here. So what's that? It's 0.42. So obviously the value factor doesn't matter. Yeah? The value factor does not is not useful for pricing the cross-section of our 25 test assets sorted by size and profitability. What about the profitability factor? So you might have a guess already. Obviously, using test assets sorted by size and profitability, it might be not surprising that both the size factor and the profitability factor matter. And indeed, what you see here, it's a highly significant t-statistic. Yeah? So what we can conclude here from this estimation, that size and profitability factors are priced in the cross-section of expected returns using 25 test assets sorted by size and profitability, which may be not surprising. But let's see what about the pricing errors. So now we have 25 test assets again, but we have k is now 3. So now we have to take the chi-square distribution with 22 degrees of freedom as a reference distribution. So the critical value for 95% probability is 33.92 according to my table here. So let's now implement the test. What's lambda? Here we have it already estimated. We can just put it into the command window and spit it out. So it's lower than before. Yeah, before we had obviously the lambda was something like 61 or 62. Now our test statistic is 50. It has decreased by a large margin actually, but still 55.20 rounded, 55.20 is still larger than the 95% probability critical value of the reference distribution, which is under the null hypothesis distributed as chi-square with 22 degrees of freedom, right? So hence, again, we have to reject the model. So this three-factor model consisting of size, profitability, and value is not capable of pricing the cross-section of expected returns correctly, since the pricing errors are jointly statistically significant. So this was what I would like to go through with you here in this lecture today. That's how we implement the Generalized Method of Moments technique, the GMM. It's for many people in finance like a black box. It's maybe not that easy to understand in the first run, but if you have if you have a good ground, a good foundation in econometrics, statistics, and some knowledge in matrix calculus, it's actually straightforward. So thank you for your attention.